Okay, so let us start with the implicit function theorem again, what we stated and proved yesterday. So, this was the theorem. R2 open set and f was from R2 to R sorry U to R with continuous partial derivative we had a point x naught y naught in U del f del y we assume does not matter, we can assume del f del x as well, x naught y naught greater than 0 or less than 0 and f of x naught y naught is the level curve some constant, we put it 0. The statement says that then there exists epsilon greater than 0 and g from x naught minus epsilon to x naught plus epsilon to u actually how did I state it, g x naught minus epsilon such that one f of x g x equal to 0 for all x in this interval and of course g of x naught is y naught and second was we get since f is smooth enough we also get g is smooth which is g is differentiable. Well, so we have proved it. Now, if you look at the proof, then actually nothing changes. Okay, let me write this R2 as R cross R, correct? I can write R2 as R cross R. So, if it is a function from R cross R to R. And if I have del f del so we have emphasized it again yesterday that we could actually have okay for timing let it remain as del f del y and I will have an interval around x naught. So, this was the picture. Where I can make g defined and for each g as there is a unique tangent for each g I can have a unique y and I can prove that g is differentiable. Now, if you look at the proof yourself, if I instead of r cross r, if I put r n cross r and in that case I will have u here and x naught is a vector in R n, y naught still a point in R, and I have instead of del f del y, let me say del x I x naught y naught, each of them positive, and f of x naught y naught 0. The proof goes verbatim, but here I have to change the interval to a neighborhood of x naught. And that is it. This proof will go exactly same. If you work it out, this is a statement for R n cross R. Well, the general implicit function theorem is not from R n to R, R n cross R to R, it is actually R n cross R k to R n. So, n and k you can take arbitrary, and then y naught where x naught belongs to R n and y naught belongs to R k. So, in this case, this part I will have f a function of so f you write as f1, f2, fn, then fn plus 1 to n plus k, and here you take I equal to 1 to n, j equal to 1 to n. The first component wise partial derivatives are continuous, and this fellow x naught, instead of greater than 0 I will say determinant is greater than 0 or non-zero. Then I will have the same, and now it will take values in R n such that the same thing happen, and g x naught, g of x naught is y naught, g is differentiable with j g at x naught is del f I del x j at x y inverse, this is n cross n, del f I del x j I equal to 1 to n. Let me put it k here, k equal to 1 to j equal to 1 to k. Well, this is R n, yeah. So, this is the version of implicit function theorem, the most general form of implicit function theorem. I think I have messed up with some n and k. G will be from x naught epsilon to R n. So, I should take acha. So, instead of in the first version, if you assume this instead of del f del y, if you prove it for del f del x, you will get this, because the final matrix will be n cross k, and that is the derivative of G. And this proof is actually does not follow what we wrote down earlier, but this proof follows from the earlier version. Follows from u from Rn to R to R version by induction. So, you have to do induction on k and n both. So, I will not prove that theorem, because this is just mere formality, this is an induction argument. But if you are really interested, this is available, very nicely available in this source, which is available in archive.math/pdf, and the number is 12122066. So, if you check this link, you will find a proof by induction from the previous version. This proof will be just done by induction, and it is written very nicely here. And there is some other comments about implicit function theorem, and I want all of you to check that source. So, this is all about the statement and proof of implicit function theorem. So, what you want to do now? We want to do some applications, and if you talk about the applications of implicit function theorem, I mean the entire subject of differential geometry that thrives on the statement of implicit function theorem. So, you will need, you can talk about in a full course the application of implicit function theorem, and in different areas. But for this course, we will take up only two very important one in part of the syllabus of any differential calculus course. First of them is Lagrange multiplier methods, and second is inverse function theorem. Inverse function theorem, I will talk about it later, maybe next lecture. But for today, we will illustrate an application of direct application of implicit function theorem in so called Lagrange multiplier method. So, let us talk about Lagrange multiplier method. What it says, it is about the problem of finding extrema, maximum value or minimum value of a function f from Rn to R, or let us say f from u to R, u in Rn, open set, to find maximum or minimum, in general extremum of f we have done this problem, but now there is one constraint, that is subjected to so you can think of it like this, that I have a surface or curve whatever of G. F is defined on entire R2, but you have to find the extremum of F with respect to this constraint Gx equal to C. For example, in the assignment we will find many. So, we will solve this example after we develop. Say, let us say find minimum distance from point let us say something minus 5 0 to the curve or to the parabola y square plus 4x equal to 0. So, what is the problem? It is a two dimensional problem. So, I have this parabola y square plus 4x equal to 0. So, this is a parabola and I have a point minus 5 0 here. I have to find the minimum distance. So, from this point you can draw these straight lines, different straight lines to parabola. You have to find the shortest one. So, this is particularly you find the, so your fx will be, f of xy will be minus 5 minus x square y minus 0 y square. So, this function has to be minimized subjected to y square plus 4x equal to 0. This is a typical example of Lagrange multiplier method, and it can be done. Okay, I will. This is from R2 to R, function from R2 to R. But again, as I said, if you understand from R2 to R, you know everything from Rn to R. Of course, I have to take function taking values in R, otherwise maximum minimum does not make sense. Like implicit function theorem, if R2 to R concept is clear, from Rn to R is just formalities. So, I will illustrate both, but as for the illustration of the method is concerned, I will take u in R2 like this example. So, let us see how do we solve this general problem. So, how do we go about it? We have f and we have some constraint, and as I said, we are going to use implicit function theorem. How? Well, suppose x naught y naught, this is an extremum, that is maximum or minimum of f subjected to g x naught y naught in C. Suppose we have a extremum, we may not have. So, we will assume nice property about f and g. Both f and g has continuous partial derivatives in U. This I need to apply implicit function theorem. Okay. Let me get back to the example. What we will do? If I do not know the Milagliano-Ampere method, what I will do? What I will do is simply this, that I am looking for the curve y square equal to 4x. So, on this curve y square equal to minus 4x, so x has to be negative. So, actually the problem boils down to, for this example, that you look at this function f x minus 5 minus x, that is minus I can consume in the square, and then y square equal to minus 4x. So, basically this y square part, that y part I can avoid by replacing by a function of x only, which is 4x here, minus 4x here. Now, what does implicit function theorem says? That okay, this is a level curve. Every level curve, if it is a nice function, then it may not be a graph. So, this level curve is a graph of the function x y square equal to minus 4x. So, y equal to root over, so 2 minus x, x in, x has to be negative to make this sense. So, this is a graph of this function locally and plus minus. So, two functions are there, one this and another is x minus this thing. Implicit function theorem says that okay, this level curve I can locally look at a graph of some function, because if I look at the upper portion, this is the parabola. If I look at some portion here, then I can define a function g. For this portion I can define a function g, which is x plus 2 root over minus x, and for this portion the second one, this one. So, I can replace this condition f x y and g x equal to c by a function of x only. So, that is the entire idea, and implicit function theorem I can do it because I have assumed f and g has continuous partial derivative. So, the problem by implicit function theorem in a neighborhood of x naught y naught, let us say theta, we have y equal to some function g x, g from theta to r, right. So, the problem reduces to finding extremum of because we are only interested in local maximum, local extremum g x subjected to which one? g x equal to constant. This is a function of x only. So, these here I have used implicit function theorem in a neighborhood of x naught y naught, because I have assumed f and g both has continuous partial derivative. So, if you understand this part, next thing is just again, because I have made it a function of x only. So, it is again finding maxima or minima for real valued function. Let us say two valued function, so partial derivative will be involved, and then I have to put condition that g does not vanish at the partial derivative of g does not vanish at x naught y naught. So, I should have del g del y x naught y naught not equal to 0, supposing this is an extremum. So, why bother too much? Let us say this is not equal to 0, or let us say greater than 0 without loss of generality in a neighborhood. Of x naught. And then I can express y as g x, and the problem reduces to function of one variable, and we know that. I will illustrate it in the next lecture. So, we will continue from here. Thank you.